There is a question so fundamental, so disorienting in its implications, that most scientists prefer not to ask it directly. Not because they are afraid of the answer, but because they are not entirely sure the question even makes sense. When did the universe begin? The standard answer, the answer printed in textbooks, recited in classrooms, embedded in the opening line of nearly every cosmology documentary ever made, is 13.8 billion years ago. There was a Big Bang. There was a moment of origin. A birthday. A before and an after. But what if that answer, while technically correct, is asking entirely the wrong question? What if the universe was never actually born? Not in the sense that it always existed, stretching backward through an infinite corridor of identical ticking seconds. That would be strange enough. But stranger still is the possibility that the concept of a beginning, of a moment zero, a first instant, a cosmic birth, may be a category error. A human imposition on a reality that does not recognize time the way we do. Consider what we actually mean when we say something begins. A fire begins when the match strikes. A life begins at a first breath, or a heartbeat, or a moment of conception, depending on who you ask. In every case, something begins inside time. It begins within a pre-existing framework of before and after. It crosses a threshold that already exists. But the universe did not begin inside anything. If the Big Bang is the origin of space, matter, and energy, then it is also, necessarily, the origin of time itself. And if time itself began at the Big Bang, then the question, what happened before the Big Bang, is not a deep question waiting for a deep answer. It may be, as Stephen Hawking once put it, like asking what lies south of the South Pole. There is no south of the South Pole. There may be no before the Big Bang. And yet, and here is where the ground begins to shift beneath your feet, this does not mean the universe simply appeared from nothing. It does not mean the question is closed. It does not mean we understand what actually happened. Because three of the most rigorous, mathematically serious frameworks in modern theoretical physics, frameworks developed not by mystics or philosophers but by the same people who gave us quantum field theory, general relativity, and the Standard Model, all converge on the same extraordinary possibility. That the universe may not have had a beginning in any meaningful sense of the word. That time, as we experience it, flowing, directional, relentless, may be a feature that emerged from something deeper. Something timeless. Something that was never born and can never die, because the concepts of birth and death require time, and what we are describing precedes time itself. This is not metaphysics. This is physics. And the story of how we got here, how the question of cosmic origins dissolved, reformed, and dissolved again across a century of extraordinary science, is one of the strangest and most humbling stories in the entire history of human thought. This is the story of what happens when you ask not just when the universe began, but whether beginning is even the right word. What we think we know, and why we think we know it. To understand why the idea of a cosmic birth might be wrong, we first have to understand why we believed in it so completely. The story begins, as so many stories in modern cosmology do, with a Belgian priest. In 1927, Georges Lemaitre was not the most famous physicist in the world. That distinction belonged to Albert Einstein, who had by then already produced both special and general relativity, overturned 2 centuries of Newtonian mechanics, and become the closest thing the 20th century had to a scientific celebrity. Lemaitre was an astronomer, a Catholic priest, and a man who took both vocations with complete seriousness. He had been working through the implications of Einstein's general relativity, specifically its field equations, and he had noticed something that Einstein himself had missed, or rather, had deliberately avoided. The equations did not describe a static universe. They described a universe in motion. Specifically, a universe that was either expanding or contracting. Einstein, committed to the philosophical intuition that the cosmos was eternal and unchanging, had inserted a mathematical fudge factor, the cosmological constant, specifically to force his equations to produce a static result. He would later call this the greatest blunder of his career. But in 1917, the idea of a universe with a beginning was too theologically loaded, too philosophically uncomfortable, to entertain. Lemaitre entertained it anyway. If the universe is expanding, he reasoned, then running the equations backward through time produces a universe that is progressively smaller, denser, and hotter. Run it far enough back, and you arrive at a moment of extraordinary compression. A single point, or something functionally equivalent to a single point, from which everything emerged. Lemaitre called it the hypothesis of the primeval atom. He described it in a 1931 paper as the cosmic egg exploding at the moment of the creation. The language is striking, a priest describing creation in the vocabulary of physics, making no attempt to separate the scientific claim from its theological echo. Einstein, when he finally heard Lemaitre present the idea in person, reportedly said, "Your calculations are correct, but your physics is abominable." He would change his mind. In 1929, Edwin Hubble published the observational evidence that settled the question. Distant galaxies were receding from us, and the farther they were, the faster they were receding. The universe was not static. It was expanding in every direction simultaneously, as though every point in space was moving away from every other point. Not like an explosion with a center, but like the surface of an inflating balloon, with no edge, no center, just continuous expansion. If the universe is expanding now, it was smaller yesterday. Smaller still last year. Smaller still a million years ago. 13.8 billion years ago, the math runs out, or rather, the math produces answers that our current physics cannot interpret. Temperatures and densities that approach infinity. A singularity. A moment beyond which the equations of general relativity simply break down. This is the Big Bang. Or more precisely, and this distinction will matter enormously, this is the point at which our description of the Big Bang breaks down. The Big Bang is not a theory about what happened at the very beginning. It is a theory about what happened after the very beginning, after the first meaningful instant, after conditions became such that the physics we understand could take hold. What happened at the singularity itself, at the moment our equations reach infinity, is precisely what the theory does not, and cannot, tell us. In 1949, the astronomer Fred Hoyle, a vigorous opponent of the expanding universe model, appeared on BBC Radio and inadvertently gave Lemaitre's idea its enduring name. These theories, Hoyle said with audible contempt, were based on the hypothesis that all the matter in the universe was created in one Big Bang at a particular time in the remote past. Big Bang. The name stuck. Hoyle meant it as a dismissal. History received it as a christening. By the 1960s, the Big Bang model had accumulated overwhelming observational support. The cosmic microwave background radiation, the faint afterglow of the early universe's heat, cooled over 13.8 billion years to a temperature of just 2.7 degrees above absolute zero, was discovered accidentally by Arno Penzias and Robert Wilson in 1965. The two Bell Labs radio astronomers had been trying to eliminate a persistent hiss from their antenna. They cleaned the equipment. They chased away the pigeons nesting inside the horn. They removed, with some delicacy, what their notes describe as white dielectric material deposited by the pigeons. The hiss remained. It was the echo of creation. They won the Nobel Prize. The Big Bang was confirmed. The universe had a beginning. The question of cosmic origins appeared, at least on its surface, to be answered. And yet there was a problem. Several problems, in fact. Problems so severe that within 2 decades of the Big Bang's confirmation, the model's own architects were already dismantling parts of it. Why the birthday might be an illusion. The first problem is called the singularity problem, and it is both the most obvious and the most philosophically devastating flaw in the standard Big Bang model. At time zero, at the precise moment of the Big Bang, general relativity produces a mathematical singularity. Density becomes infinite. Temperature becomes infinite. The curvature of spacetime becomes infinite. Every physical quantity that our equations are designed to describe flies off toward infinity, which in the language of mathematics is a polite way of saying, the theory has stopped working. A singularity is not a description of something real. It is a description of the limits of a theory. When the equations of general relativity produce a singularity, they are not telling you that the universe was infinitely hot and dense. They are telling you that general relativity does not apply to that regime, that something else was happening, something that a different, deeper theory would be needed to describe. This is not a minor caveat. It is a fundamental admission. The Big Bang model, in its standard form, does not describe the beginning of the universe. It describes the universe from a fraction of a second after whatever the beginning was. The actual moment of origin, time zero, is precisely where our best theory of gravity fails. Roger Penrose and Stephen Hawking formalized this in the late 1960s with the Penrose-Hawking singularity theorems. These were not speculative arguments. They were rigorous mathematical proofs, derived directly from the equations of general relativity. Under very general conditions, any universe like ours must contain a singularity. Must, in the past, have had a moment at which the theory breaks down. Hawking spent much of the next 2 decades trying to get rid of it. The second problem is subtler, but in some ways more unsettling. It is called the initial conditions problem. The universe, as we observe it today, is not random. It is not a chaotic mess of matter and energy distributed in whatever configuration chance happened to produce. It is extraordinarily, suspiciously ordered. The laws of physics are precisely calibrated. The constants of nature, from the strength of gravity to the mass of the electron, take values that permit the existence of atoms, stars, galaxies, and ultimately life. Change any of them by a small fraction, and you get a universe of pure hydrogen, or a universe that collapses back on itself within seconds, or a universe of undifferentiated plasma with no structure whatsoever. Why these values? Why this configuration? The standard Big Bang model has no answer. It does not explain the initial conditions of the universe. It takes them as given, as inputs, not outputs. The universe began in this precise, highly ordered state, and from that state it evolved to produce everything we see. But the model itself has nothing to say about why the beginning was the way it was. This is known, in the dry vocabulary of theoretical physics, as the fine-tuning problem. And it is, when you sit with it long enough, a genuinely extraordinary puzzle. The universe appears to have been set up, calibrated, arranged, in the specific way required for complexity to emerge. If the Big Bang was truly a beginning, truly a moment of spontaneous origin, then this calibration is either the most staggering coincidence in the history of existence, or evidence of something we do not yet understand. There is a third problem, equally serious. It is called the horizon problem. Look at the cosmic microwave background, the afterglow of the early universe, in any 2 directions in the sky. Measure the temperature. It will be the same, to within 1 part in 100,000, in every direction you look. The universe, at the moment the CMB was produced, was in perfect thermal equilibrium across its entire extent. Thermal equilibrium, the state where 2 regions have the same temperature, requires that those regions have been in contact. They must have had time to exchange heat, to communicate, to reach a shared state. But in the standard Big Bang model, the regions of the early universe that produced the CMB in opposite directions of the sky were never in contact. They were too far apart. Not even light, traveling since the first instant of the Big Bang, had had time to cross from one to the other. So how are they the same temperature? The answer, proposed by Alan Guth in 1980, was inflation. A brief, extraordinarily violent period of exponential expansion in the universe's first fraction of a second, so rapid that a region smaller than a proton expanded to a volume larger than the observable universe in less time than it takes light to cross a single atom. This solved the horizon problem. The regions that appear causally disconnected today were once, before inflation, in intimate contact. The uniformity of the CMB is a snapshot of that early intimacy stretched across the sky. Inflation is one of the most successful ideas in modern cosmology. It also, and this is where things become genuinely strange, may have eliminated the beginning entirely. Eternal inflation and the universe with no edge in time. Alan Guth did not design inflation to challenge the concept of a cosmic beginning. He designed it to solve the horizon problem and the flatness problem and the magnetic monopole problem, 3 specific, technical puzzles in standard Big Bang cosmology. And it solved all 3 with remarkable elegance. But as other theorists began exploring inflation's implications, something unexpected emerged. In 1983, Andrei Linda, a Soviet physicist then working at the Lebedev Physical Institute in Moscow, extended Goose's inflationary model. What Linda found was that inflation, once started, does not stop cleanly. It does not inflate the universe uniformly and then switch off, as Goose's original model implied. Instead, inflation is a quantum process, and quantum processes are inherently probabilistic. In any given region of space, inflation can end. But quantum fluctuations will always cause inflation to continue in neighboring regions. And as long as the inflating regions expand faster than the non-inflating regions shrink, inflation as a whole never ends. The universe we inhabit, the observable universe, the 93 billion light-year bubble of space we can detect, exists in a region where inflation ended approximately 13.8 billion years ago. But beyond our bubble, on scales so vast they are effectively inaccessible to any observation, inflation continues. It has always continued. It will always continue. Linda called this eternal inflation. And eternal inflation has a consequence that is difficult to overstate. If inflation is eternal in the future, if it never fully stops, then it is almost certainly eternal in the past as well. The mathematics of eternal inflation does not produce a clean beginning. It produces an infinite, self-reproducing structure in which new regions of space are constantly budding off from the inflating background, each region beginning its own post-inflationary evolution, each region potentially containing its own physics, its own constants, its own version of the laws of nature. The universe, not our universe, but the larger structure of which our universe is one bubble, has no beginning in this picture. It is not eternal in the simple sense of extending backward through infinite identical time. It is eternal in a deeper, stranger sense. The question of when it started may simply not be answerable, because the structure of time itself breaks down at the boundary of inflation. In 2003, Arvind Borde, Alan Guss, and Alexander Vilenkin published a theorem, the BGV theorem, that appeared to cut off this escape. Their proof showed that any universe with an average positive expansion rate must, when traced back in time, hit a boundary, a beginning. No matter how far back you extend an inflationary cosmology, you eventually reach a point before which the spacetime description breaks down. For a brief moment, it seemed as though the beginning had been restored. But the BGV theorem is a theorem about classical spacetime, about the regime where general relativity applies. And general relativity, as we have already established, is precisely what breaks down near the beginning. The BGV theorem does not tell us what happened at or before that boundary. It tells us only that our current description runs out. The boundary is not necessarily a beginning. It may be a transition. Hawking, Hartle, and the no-boundary proposal. In 1983, Stephen Hawking and James Hartle published a paper that may be the most philosophically radical proposal in the history of cosmology. They called it the no-boundary proposal. To understand what they were suggesting, we need to briefly inhabit a concept that is deeply counterintuitive but mathematically precise: imaginary time. Time, in our ordinary experience, flows in one direction. It has a before and an after. Mathematically, we can represent it as a line, a real number line, extending from the infinite past to the infinite future. The singularity of the Big Bang appears as an endpoint of this line. A wall. A moment before which the line does not exist. Hawking and Hartle asked, what happens if you treat time, in the vicinity of the Big Bang, as a mathematical complex number, incorporating what mathematicians call an imaginary component? This is not a metaphor. It is a specific mathematical technique, used in quantum mechanics, called a Wick rotation, replacing the time coordinate with an imaginary time coordinate in order to make certain calculations tractable. When you apply this technique to the universe's earliest moments, something remarkable happens. The distinction between time and space dissolves. Near the beginning, in this mathematical framework, there is no separate time direction. There is only space, a smooth, curved, four-dimensional space with no edges, no boundaries, no singularity. The universe, in imaginary time, does not have a beginning any more than the surface of the Earth has an edge at the South Pole. You can travel as far south as you like. Eventually you reach the South Pole. But the South Pole is not a wall, not an edge, not a boundary. It is simply the point at which the concept of south ceases to apply. The Big Bang in Hawking and Hartle's framework is the South Pole of the universe. Not a beginning in any meaningful sense. A smooth geometric point at which the concept of before simply ceases to apply. Hawking articulated this with characteristic directness. The boundary condition of the universe is that it has no boundary. The universe did not begin. The universe does not have a beginning in the way a fire has a beginning or a life has a beginning. It simply is a closed, self-contained structure in which the question of what came before is as meaningless, mathematically, as the question of what lies south of the South Pole. This is not a comfortable conclusion. It sits badly with our intuitions, which are built from a lifetime of experience in a world where everything has a cause, everything has a before. But our intuitions, as the history of physics repeatedly demonstrates, are a poor guide to fundamental reality. The no-boundary proposal is not without its critics. The use of imaginary time is a mathematical trick, a tool for making calculations possible, and there is genuine debate about whether it corresponds to physical reality or merely to a useful mathematical fiction. Hawking himself was sometimes deliberately ambiguous on this point. And yet the no-boundary proposal has survived decades of scrutiny. It makes specific, testable predictions about the spectrum of the cosmic microwave background. It provides a natural explanation for the initial conditions problem, the fine-tuning of the universe's starting configuration, because in a no-boundary universe, the initial conditions are not conditions at all. They are simply the geometry of a smooth, self-contained space. They do not require explanation from outside. They are not imposed. They are intrinsic. The block universe, quantum gravity, and the disappearance of time itself. The no-boundary proposal is radical, but it is not the most radical possibility on the table. That distinction belongs to a cluster of ideas emerging from the intersection of quantum mechanics and general relativity, the two great unfinished revolutions of 20th century physics, still unreconciled, still pointing at each other across a conceptual chasm that no theory has yet fully bridged. The problem is this: quantum mechanics and general relativity are both extraordinarily accurate descriptions of reality. Quantum mechanics governs the behavior of subatomic particles with a precision that is, by some measures, the most accurate in the history of science. General relativity governs the behavior of spacetime, gravity, black holes, the large-scale structure of the cosmos, with comparable precision. But they are incompatible, not approximately incompatible. Fundamentally, mathematically, irreducibly incompatible. When you try to apply quantum mechanics to the gravitational field, to quantize gravity, as physicists say, you get nonsense. The equations produce infinities that cannot be removed. The theory breaks down. This is the quantum gravity problem, and it is the deepest unsolved problem in theoretical physics. But here is what is relevant to our question today. In 1967, two physicists, Bryce DeWitt and John Wheeler, attempted to construct a quantum theory of the universe as a whole. Their equation, the Wheeler-DeWitt equation, is one of the strangest objects in all of physics. It describes the quantum state of the entire universe, the wave function of the universe, the quantum mechanical description of all of space, all of matter, all of energy at once. And the Wheeler-DeWitt equation contains no time variable. None. Time does not appear in the fundamental equation governing the quantum state of the universe. This is not an oversight. It is not a simplification. It is a direct consequence of the mathematics of quantum gravity, the way the quantum description of space necessarily absorbs the time variable, leaving an equation that is, technically, timeless. The universe's wave function does not evolve through time. It simply is. A static, timeless mathematical object that contains, encoded within its structure, all possible configurations of space, matter, and energy. All possible histories. All possible times. Time, the time we experience, the flow from past to future, the arrow that points from the Big Bang to the heat death, is not fundamental in this picture. It is emergent. It arises from the correlations between different parts of the universe's wave function. It is, in a very precise sense, a relationship rather than a thing. Carlo Rovelli, one of the architects of loop quantum gravity, one of the leading candidates for a theory of quantum gravity, has argued this point with particular force. Time, he writes, is not a feature of the universe. It is a feature of our ignorance. We experience time because we have limited information about the full quantum state of the universe. If we knew everything, if we could somehow read the entire wave function, the flow of time would dissolve. There would only be the timeless wave function, containing all moments simultaneously. In this picture, asking when the universe began is like asking what is north of the North Pole. The question applies a concept, temporal location, to a context in which that concept has no meaning. The universe was not born, because birth is an event in time, and time at the deepest level may not exist. Loop quantum cosmology and the world before the bang. Not everyone is comfortable with a timeless universe. And not everyone agrees that the singularity at the heart of the Big Bang is a genuine termination, a point beyond which time simply does not extend. Some of the most rigorous work in modern theoretical physics suggests a different possibility entirely, that the Big Bang was not a beginning. It was a bounce. Loop quantum cosmology is a framework developed primarily by Abhay Ushtekar, Martin Bojewald, and their collaborators over the past 2 decades. It applies the mathematical tools of loop quantum gravity, a specific approach to quantizing spacetime, to the cosmological context. And what it finds is that the singularity of the Big Bang, when treated quantum mechanically rather than classically, does not exist. In general relativity, tracing the universe backward toward the Big Bang, density and curvature increase without limit until they reach infinity, the singularity. But loop quantum cosmology introduces a minimum length scale, the Planck length, approximately 10 to the minus 35 meters, below which the concept of continuous space breaks down. Space, in this framework, is not smooth and continuous all the way down. It is granular, discrete, made of finite, indivisible quanta. And when density approaches the Planck density, when the universe is compressed to the point where these quantum grains of space are packed as tightly as the theory allows, something extraordinary happens. The gravitational force, which in classical general relativity would continue to compress the universe toward a singularity, becomes repulsive. Gravity at the Planck scale pushes back. The result is not a singularity. It is a bounce. The contracting universe reaches a minimum volume, still unimaginably small, but finite, and then rebounds, expands, begins the evolution that we, looking forward through 13.8 billion years of cosmic history, call the Big Bang. But what was contracting before the bounce? In the most natural interpretation of loop quantum cosmology, the answer is a previous universe. A cosmos that preceded ours, that lived its own vast history of expansion and structure and possibly life, that eventually contracted under its own gravity through a big crunch, and that, rather than terminating in a singularity, bounced into our Big Bang. This is the Big Bounce. And in the cyclic frameworks built on this idea, there is no beginning. There is a sequence of universes, each born from the collapse of its predecessor, extending backward through time without limit. Roger Penrose has proposed a different but structurally similar cyclic model, called conformal cyclic cosmology. In Penrose's framework, the universe does not collapse and bounce. Instead, the very distant future of the universe, the cold, dark, black hole-dominated state that thermodynamics dictates the cosmos will eventually reach, is mathematically equivalent, at the deepest level of geometry, to the hot, dense state of a new Big Bang. The end of one universe is the beginning of the next. Not because anything bounces or collapses, but because, at the level of pure geometry, the two states are the same. Penrose calls the boundary between one aeon and the next a crossover. Information, specific patterns encoded in the geometry of the universe at its end, can propagate through the crossover, leaving faint imprints on the cosmic microwave background of the next aeon. In 2010, Penrose and his collaborator Vahey Gurzadian reported finding what they believed were circular patterns in the CMB, concentric rings of slightly different temperature that they interpreted as echoes of black hole collisions in a previous aeon. The claim remains highly controversial. Other cosmologists have disputed both the statistical significance of the rings and their interpretation. But the possibility, the sheer audacity of the possibility, that we can observe evidence of a universe that preceded ours in the cosmic microwave background is one of the most extraordinary ideas in modern cosmology. And it is an idea that requires no beginning. In Penrose's model, the sequence of eons extends backward without limit. Each universe is born from the mathematical ghost of its predecessor. There is no first aeon. There is no moment of creation. There is only the endless succession of cosmic cycles, each one a complete universe in itself, together forming a structure that is, in the deepest sense, eternal. Everett, Hawking, and the scientists who challenge time itself. It is worth pausing here, in the midst of equations and bounces and imaginary time, to remember that these ideas were not produced by machines or algorithms. They were produced by people. Hugh Everett III was 30 years old when he submitted his doctoral thesis at Princeton in 1957. His advisor was John Wheeler, the same Wheeler who would later co-develop the Wheeler-DeWitt equation. Everett's thesis proposed what is now known as the many worlds interpretation of quantum mechanics. The idea that the wave function never collapses, that every quantum event produces a branching of the universe into multiple histories, that all possible outcomes of every quantum measurement actually occur in separate, equally real branches of reality. Niels Bohr, the patriarch of quantum mechanics, rejected it. The Copenhagen interpretation, the standard view that the wave function collapses upon measurement, was the established orthodoxy, and Bohr's dismissal carried enormous weight. Everett left physics. He spent his career in defense research. He died of a heart attack at the age of 51, in 1982, having never seen his ideas taken seriously within the mainstream of his field. He never knew that the many worlds interpretation would be rehabilitated in the 1970s and 1980s, and that by the early 21st century it would be the preferred framework of many, perhaps most, working physicists in quantum foundations. He never knew that the no-boundary proposal, Hawking's greatest contribution to quantum cosmology, was, in a deep sense, built on the foundations his thesis had laid. The wave function of the universe, the timeless quantum state that Hartle and Hawking wrote down in 1983, is a many-worlds object. It does not describe one history. It describes all possible histories of the universe simultaneously, each with its own quantum amplitude, each a real branch of the cosmic wave function. Everett died unrecognized. Hawking went on to become the most famous physicist of his generation, his no-boundary proposal a cornerstone of modern quantum cosmology. History is not always fair in its timing. And then there is the quieter story of Bryce DeWitt, the man whose name appears on the equation that removed time from the universe. DeWitt spent decades working on the quantization of gravity, in an era when most physicists considered it a dead end. He developed much of the mathematical formalism that underlies modern approaches to quantum gravity. He was meticulous, technically demanding, and, by the standards of physics celebrity, almost entirely unknown to the general public. He died in 2004. The equation that bears his name, and Wheeler's, remains unsolved in any complete sense. We do not know how to extract time from the Wheeler-DeWitt equation in a way that fully recovers the time we experience. We do not know how the emergent time of the everyday world arises from a fundamentally timeless quantum state. These are open problems. They are among the most important open problems in all of physics. The scientists who asked whether the universe had a beginning did not do so from a position of comfortable certainty. They did so from positions of intellectual courage, willing to follow their equations into terrain where intuition was useless and the conclusions were deeply strange. That courage is, perhaps, the most definitely human thing about the entire enterprise. The honest reckoning. We have traveled a long way from the standard textbook answer. We began with a birthday, 13.8 billion years ago, a moment of singular beginning, the Big Bang. And we have arrived somewhere considerably stranger. We have encountered the no-boundary proposal, in which the universe has no beginning because time itself dissolves into space at the cosmic South Pole. We have encountered eternal inflation, in which our universe is one bubble in an infinite sea of inflating spacetime with no discernible starting point. We have encountered the Big Bounce, in which our Big Bang is the rebound of a previous universe's collapse. We have encountered the Wheeler-DeWitt equation, in which time does not appear at all, in which the universe's fundamental description is timeless, and time is an emergent property of our limited perspective on an eternal quantum state. Each of these frameworks is mathematically serious. Each is the product of rigorous physics, developed by some of the finest minds of the last century. And each of them arrives, by a different route, at the same extraordinary conclusion. The universe may not have been born. And yet we must be honest about what this means and does not mean. None of these frameworks has been confirmed observationally. The no-boundary proposal makes predictions about the CMB spectrum that are, in principle, testable, but the precision required to distinguish them from competing models is at or beyond the limits of current technology. Loop quantum cosmology makes predictions about the pre-Big Bang universe that are, by some calculations, in principle observable, but extracting that signal from the noise of 13.8 billion years of cosmic evolution is a task that may exceed the capabilities of any instrument we can currently imagine building. Eternal inflation, in its most developed forms, predicts a multiverse that is, almost by definition, beyond the reach of any observation, making it, in the view of some physicists, less a scientific theory than a mathematical framework. The honest answer, the answer that the science demands, rather than the answer we would prefer, is this. We do not know whether the universe had a beginning. We know that the Big Bang model describes the universe's evolution from a fraction of a second old to the present with extraordinary accuracy. We know that general relativity, traced back to that earliest measurable moment, produces a singularity that the theory itself cannot interpret. We know that quantum gravity, the framework that would be needed to describe that earliest moment, does not yet exist in a complete form. Beyond that, we are in the territory of serious, mathematically grounded speculation, of frameworks that are internally consistent, that make contact with established physics, and that cannot yet be empirically distinguished from one another. This is not a failure of science. It is science operating at its frontier, at the boundary between what we know and what we are still trying to understand. And at that frontier, the question, was the universe born, remains genuinely, deeply unresolved. In 1828, Edward Quinn completed his historical atlas, those maps with their expanding circles of known territory and their retreating clouds of mystery. Quinn believed, as his contemporaries believed, that the age of discovery was essentially complete. The clouds had lifted. The continents were mapped. There was no more land left to find. He was right about the land. But the clouds did not disappear. They simply shifted. Inward. Downward. To scales Quinn's instruments could not reach and questions his century had not yet learned to ask. We are in our own moment, in a position not entirely unlike Quinn's. We have mapped the universe, not fully, but to a degree of precision he could not have imagined. We know its age, its composition, its geometry, its history from a fraction of a second after the beginning to the present day. We know it is 68% dark energy and 27% dark matter and less than 5% everything we can see and touch and are. And we have arrived at the edge of the cloud. The question of whether the universe had a beginning is not a question about distant galaxies or exotic particles or the configuration of matter in the early cosmos. It is a question about the nature of time itself, about whether time is fundamental or emergent, about whether the concepts we use to describe events, before, after, origin, cause, apply to the universe as a whole or only to things within it. Stephen Hawking, near the end of his life, returned again and again to the no-boundary proposal, not with the triumphalism of someone who had solved the problem, but with the measured confidence of someone who believed they were looking in the right direction. The universe, he wrote, is not something that simply appeared from nothing. It is something that appeared from a quantum state, a state in which the distinction between space and time breaks down, and the question of what came before becomes as meaningless as the question of what lies south of the South Pole. Meaningless, perhaps, but irresistible, because the human mind, this small, warm, improbable instrument that the universe has somehow produced from hydrogen and time, cannot stop asking the question. Cannot rest easy with the answer that there is no answer. Cannot accept, at the level of lived experience, a cosmos that simply is, without a moment of becoming, without a first instant, without a why. Perhaps that restlessness is itself meaningful. Perhaps it is the universe, through us, trying to understand its own origins. Perhaps it is simply the character of minds shaped by a world where everything around us has a cause, reaching for a framework that cause does not enter. We do not know. And that not knowing, that precise, mathematically informed, genuinely humble not knowing, is not a gap in our understanding. It is, for now, the most honest thing we can say. The universe may have been born. It may have always existed in some form we do not yet have the language to describe. It may be a timeless quantum object from which time itself emerges, making the question of its birth a category error, a word applied in the wrong direction. What we know is that the question is real, that the people asking it are extraordinary, and that the answer, when it comes, if it comes, will not merely add a chapter to our understanding of the cosmos. It will rewrite the nature of understanding itself. You've been watching the Astrogrid. Don't forget to like and subscribe, and leave a comment to tell us what you think as we continue to push past the edges of what we know. Thanks for watching, and we'll see you next time.